थोड़ा डेलिकेटली टच कीजिए इसको, इसका थोड़ा ऊपर हाथ रखिए। जो नीचे का शू है ना, मैं लाए निकले, दूसरे कैमरे में लगाया था ना, भूल गया था। So folks, today econometrics. Right? We did a maths class. Now econometrics. Now I take you back to the idea of instrumental variable estimate. So can you somebody quickly recapitulate to me when do you use an instrumental variable estimator? What are its features? Yeah? Can somebody quickly recapitulate what do you mean by an instrumental variable estimator and when do you use an instrumental variable estimator? Yes, some of you gave me good answers last time. So, yes, when do you use an instrumental variable estimator? When there is endogeneity, when X and E are correlated. So what is an instrumental variable estimator? What's an instrumental variable first? How do you define instrumental variable? It's a variable Z which is correlated with X but not correlated with E. Right? Sure? Okay. So basically you have a model where and sure. Then you think of a variable Z such that right, and then you write or so we get beta hat right. This is we give it a name, the instrumental variable estimator, right? Whereas what is the OLS estimator? Right? Now we know that if X and E are uncorrelated, the OLS estimator is unbiased and consistent. But if X and E are correlated, then the OLS estimator is neither unbiased nor consistent. And we are arguing that the instrumental variable estimator will be both. So first let's try to prove that the instrumental variable is actually unbiased and consistent. Then we have to look at its distribution. Then we have to learn how to take hypothesis tests on the OLS estimator and the instrumental variable estimator. Right? So we have think of a model y is equal to alpha plus beta xi plus p. Now I'm going to do some sleight of hand. I'm going to do a little bit of a trick to make the calculations easier than what they should be. Right? So let me find y bar. What will y bar be? alpha plus beta x bar. Yeah? Everybody gets this? Y bar is alpha plus beta x bar. So if I subtract yi minus y bar, what will I get? I'll get this. Right? Sure? So let me now write yi minus y bar as 1. Okay? And let me write xi minus x bar as x. So when I say y, I actually mean y minus y bar. When I say x, I actually mean xi minus x bar. So I will be able to get rid of the alpha. Okay? Similarly, the OLS estimator beta hat I'll also think of z as zi minus z bar. This is the OLS. What is the beta hat IV? Yeah? This is the beta hat IV. Right? How can you argue that it will be consistent? Why should you argue that this will be a consistent estimator? Because by definition Z and E are uncorrelated and beta hat IV is really the covariance of x, y, z upon the covariance of x, z. As the sample size increases, the covariance formulae will go to the appropriate one. So it will be consistent. Let's say it's unbiased. What is unbiased? To prove unbiasedness, you have to show, just like proving unbiasedness for the OLS case, you have to show that expectation beta hat OLS is equal to beta. We know now for sure if covariance x and E is not 0, then we know for sure that expectation beta hat OLS is not equal to beta, right? Because x and E are correlated. Is that the case with the instrumental variable estimator? So now this can be written as summation zi beta xi plus ei, because that is what yi is, upon summation zi xi, right? Now take the further steps. Tell me what should go ahead. What should be the next step?
Yes, we just go with the brackets and
Okay. So this will be
get beta times that becomes 1, that becomes 0.
This in turn will be equal to, so this is this. So this is what it is. So if you open this, if you simplify this further, right? And then what will be beta hat IV? Zi and xi are fixed. Expectation zi, expectation summation zi xi. What is expectation summation zi xi? The covariance between z and x. So this is equal to 0, and therefore we show that expectation beta hat IV is equal to beta. Expectation beta hat IV is equal to beta. Right? Okay. Now, can you argue that beta hat IV will be normally distributed as well? Can you argue? You remember we argued that beta hat OLS will be normally distributed? Did we do that? Yeah, we proved that, right? So can you now argue for me also that beta hat IV will be normally distributed? Like you yourself have been able to show to me that beta hat IV will be an unbiased estimator of beta hat. Can you show me that beta hat IV will also be normally distributed? What is beta hat IV? What is the formula? Yeah? Right? Which is equal to? Yeah? So it is y1 into something plus y2 into something plus y3 into something plus etc. Each of the y's is normally distributed. So beta hat IV is also normally distributed. Right? Beta hat IV is also normally distributed. Okay. Now, so we have learned two things. Right? Okay. Now for a minute, assume that in an OLS model, X and E are indeed uncorrelated. In a OLS model, assume that X and E are indeed uncorrelated. Let's go back to that assumption. Okay, so that beta hat OLS is an unbiased estimator for beta. It's a consistent estimator. It's normally distributed estimator. So we know that if X and E are uncorrelated, again, mind you, I am talking about specific of the case that X and E are indeed uncorrelated, then beta hat OLS is normally distributed with mean beta, because expectation beta hat OLS is equal to beta. If X and E are uncorrelated, expectation beta hat is indeed equal to beta, right? And some variance sigma square into beta hat OLS, right? We'll call that variance of beta hat OLS. It's a random variance. So now let's have we derived an expression for sigma square beta hat OLS?
No, sir.
No. So let's try to do that. We know, again I am sticking to my simplified notation. Yeah? Yeah? Right? So beta is equal to beta plus summation xi ei, right? Upon summation xi ei. Or we know that beta hat is expectation beta How do we know this? How do I know this? Because of that, so beta is equal to beta. So now what will be the variance of beta at OLS? What is the variance of x? What is the variance of x in general? expectation of x minus expectation x, the whole square. The variance of x is expectation of x minus expectation x, the whole square. What will the variance of beta hat over less? So it should be yeah. Right? Because this is nothing but expectation beta hat of x. Through unbiased. Of course, x and e are correlated, this formula doesn't work. If x and e are not correlated, we are assuming specific that x and e are not correlated. Right? Okay. So, this is what? Yeah? Another way. As a direct application, this will be written put this. Over? Yeah? Sure? Okay. So now look at this. Right? This can be written as, I can take the summation xi square out and expectation of, yeah? Right? Because summation xi square is a constant anyway. So I take it out of the square of the square. Right? Okay. Now, let me just think of a simplicity x1, x2, e1, e2. The summation is a very simple thing, okay? So this can be written as expectation. That's all. Right? Into, of course, xi behind the whole square. x1 e1 plus x2 e2 the whole square. Yeah? Right? Sorry. I need to take these also. I'm sorry. Yeah? x1 e1 plus x2 e2 the whole square. Right? Now what is a plus b whole square? A square plus b square yeah? Okay? So this can be written as right? A square plus b square plus 2. I just use the expectation operator throughout. Expectation of x plus y plus z is expectation of x plus expectation of y plus expectation of z. Now the point is, what should be the next step? What can you do the next? Yeah, what should be the next step? And what can this bracket become? Can I take x1 square out of the bracket here? It's a constant. So I can write. Can I take x2 square out of the bracket? And can I take x1, x2 out of the bracket? Now you must tell me, what is expectation even square? The variance of the error term. The first error term. Expectation E2 square is the variance of the second error term. Because what is the variance of in general of E would be expectation of E1 minus expectation E1 the whole square. Expectation E1 is 0. So it will be expectation E1 square. That will be the variance. Right, so we call it sigma 1 square, variance of the first error. Right, so this becomes sigma 2 square plus, can you tell me what is expectation E1 into E2? Covariance of E1 and E2. Because covariance of xy is expectation of x minus expectation x, y minus expectation y. So covariance of E1, E2 would be expectation of E1 minus expectation E1, E2 minus expectation E2. Expectation E1 and expectation E2 are both 0. So it will be expectation E1, E2. Right? Okay. So this I will write this as 2. I give this term gamma 1. Now I'm going to make some explicit heroic assumptions, which may or may not be true in the real world. We'll develop methods of testing how we can actually check. I'm going to assume first that sigma 1 square is equal to sigma 2 square. That is, I'm going to assume that the variance of the error term is constant. Right? Okay, so what does it effectively mean? It means that if this is the conditional mean function and if this is x1 and this is x2, individual values of y can be around this, right? That will be E1. We are saying individual values of y can be around this, that's called E2. Basically the spread of E1 and the spread of E2 is the same. Right? This is making a specific assumption. It will not be true in many cases. But we are making this assumption here, and this assumption is called the assumption of homoscedasticity. Okay? Homoscedasticity. Yeah? If you call it heteroscedasticity. Okay, sigma 1 square is not equal to sigma 2 square. You have heteroscedasticity, but we are specifically assuming homoscedasticity. Okay, we are specifically assuming homoscedasticity. See, so this is x1. This is the conditional mean of y given x equal to x1. And this is how individual values of y1 can vary around x1 at the conditional mean. Right? This is x2. This is the conditional mean of y given x equal to x2. And this is the spread of individual values of y around x2. Right? What we are saying is the spread of the values of y around this line at x1 and the spread of the values of y around this line at x2. If we draw spreads, then the spreads will be in the same funnel. There will be two parallel lines which will contain the spread. So the variance will not either. So we are looking at situations where, say, this is much more broadly spread, or that this is less spread up. Right? Is this clear? Okay. I am going to also assume that E1 and E2 are uncorrelated. I am going to assume that E1 and E2 are uncorrelated. Okay? So So I'm going to assume that okay, which is called the assumption of no autocorrelation. Which is called the assumption of no autocorrelation. Assumption of no autocorrelation. Okay? So if this assumption is not satisfied, we say there is autocorrelation between E1 and E2. If E1 and E2 are correlated, we say there is autocorrelation.
So, but for this to happen, basically x1 and x2 should be then uncorrelated because E1 is correlated
Not
to
necessarily.
x2.
No.
But the E1 is correlated to x1 and E2 is correlated to
No,
x2.
E1 is not correlated to X1. That's a specific assumption that E and X are independent. Right? Okay. So, covariance E1 E2 is equal to 0. So, under that assumption, the first assumption means that these are both equal. I can call them the common number sigma square. Right? And this part becomes 0. Right? This part becomes 0. Sure? Because gamma 1